I welcome you to this week's Maritime Information Update. My name is Paul Koch. I'm on the team Maritime Informatics, and I will be the moderator for today. The presentation will be held by my dear colleague Mert, who is a former, let's say, mechanical engineer, now heavily occupied with working with machine learning and AIS data within our team. Before we start the presentation, a few words for you. The presentation is recorded, so I would kindly ask you to keep the camera switched off and the microphone switched off. If you have any questions during the presentation, you can just post them in the chat and we will pick them up after the presentation. Also, after the presentation, you have the option to unmute yourself and ask a question directly. I think with this introduction, Mert will tell us something today about extracting vessel-to-vessel encounters from historical AIS data for machine learning applications. So with these words, Mert, the stage is yours.
Thank you very much, Paul, for the kind introduction. Yeah, as Paul mentioned, today we will be talking about vessel-to-vessel encounters, extracting them from the historical AIS data, the methodology that we used, and how the data set that we created can be used for future data analysis jobs or machine learning applications. So, as always, I would like to start my presentation with briefly mentioning what is AIS data, in case in the audience there is people that are not familiar with it. AIS data is like the full word automatic identification system, is a maritime tracking technology that transmits vessels' position, speed, or identification data in real time. So we have two different data in the AIS, the dynamic information and the static information. The dynamic ones that changes are the ones that change over with timestamp. And the static ones are the ones that are not frequently changing, let's say. And the dynamic information involves latitude, longitude, heading, course over ground, speed over ground of the vessel, rate of the turn, and the timestamp, of course. And here at CML, we have 4 years worth of historical AIS data that we can analyze to gain insight into the maritime traffic. So without further ado, before talking about the methodology that we use to extract vessel-to-vessel encounters, I would like to talk about how do we define an encounter. I also prepared a small video for it. So we define an encounter if two vessels are close to each other spatially, and they are also close to each other in a temporal way, while they are also close to each other spatially. And also, we say they need to trigger a callback rule given by the definitions that on the paper that I have cited here. And on the right side, you can see the callback rules that we have specifically extracted in our encounters. So if two vessels are close to each other spatially and temporally, and they also trigger one of the rules that are shown on the right side, which are head-on crossing and overtaking, then we take that as an encounter into our database for further analysis. And why did we need to extract encounters at all from the historical AIS data? Before dealing with encounters, I personally was heavily involved in extracting maritime traffic from the AIS data, because I imagined if we can extract the maritime traffic, we can find similar trajectories to each other that we can use for machine learning applications, for trajectory prediction, for risk analysis and everything, just by looking at the historical trajectories. Then I have encountered the collision data that I am going to show you here. Just a small information, this collision that is shown here is between a vessel that is going underway using engine and a barge vessel that is being towed by a tug. And at the time of the encounter, the barge vessel does not have any AIS data associated with it. We only have AIS data from the black vessel and the yellow vessel, and we are assuming the location of the barge. Most probably, the black one also had no idea that there's a green vessel there that is being towed. And here you can see the trajectories of this encounter, of this, let's say, collision. And yeah, it is a crystal clear collision, no action has been done to alter the course because most probably it had no idea that there was a ship here. And on the right-hand side, you see the anomalies that we have extracted from this data. As I said before, we were focused on maritime traffic, and we trained machine learning models to extract course over ground and speed over ground anomalies based on the movements of past captains that have traveled the same route. And not to our surprise, our model was able to find anomalies, but the anomalies have been only found after the collision happened. You see the black ones are the course over ground anomalies, and the green one is the speed over ground anomaly, just before the collision. Now, the interesting thing here is both of the vessels are going in directions with speeds and headings that are normal when you look at the historical AIS data. However, it's a risky situation because they're actually on the collision course, which made us realize that the anomaly models that are specifically trained on maritime traffic will not be able to completely assess the risky situation of an encounter. Thus, we decided to extract the encounters to come up with an even better collision risk index. Here is the methodology that we used. It's pretty straightforward. We chunk the AIS data daily. Why do we do that? Because we didn't want to just feed the whole AIS data of 4 years into one Python script that it would use a lot of RAMs. And since encounters mostly happen in smaller time frames, let's say 1 to 2 hours, 0 to 2 hours, it made sense to chunk them daily, which also meant we lost some encounters and they happened around 12 o'clock and continued in the next day. But that was a trade-off we were willing to take considering the sheer amount of data we have. And afterwards, after we feed in the data daily, we first do a spatial clustering using the line triangulation, which basically creates edges between points that are close to each other. And then furthermore, we checked this connectivity with temporal conditions. If they're actually also temporally close to each other, we basically take differences of the timestamps of the AIS reports. And then as the last step, we check the connections between, if they are between different vessels. So if it is an encounter, that means their MMSI should be different. So we basically check their MMSI difference. And afterwards, due to the limitations of the Delaunay triangulation into understanding the complete encounters, we have one more step for combining the extracted encounters based on the MMSIs of the involved vessels, which I will explain a little bit more in detail in the next slide. Afterwards, we have the complete encounter trajectories, which we use for interpolation of the data. And this interpolation is unfortunately necessary since we are going to do callback assessment, and callback assessment is done on, let's say, pairs of points, 1 point from the own ship, 1 point from the target ship, and they need to be at the same timestamp so that we can assess the callback safely. Why I say unfortunately for interpolation? Because it always introduces some inaccuracies to the data since we need to define the interpolation method. But in order to mitigate the risk of having inaccuracies in the data, for the third step, the temporal connectivity assessment, we left a very strict condition of 200 seconds. So basically, we assumed there wouldn't be so big of a heading change in that time span between consecutive points. And yes, the limitations of Delaunay triangulation. So on the left-hand side, I prepared 2 synthetic trajectories to show how the triangulation works. The first trajectory is shown with circles and the timestamps, and the other trajectory is shown with squares. And when you apply Delaunay triangulation, you get the edges that are shown here. Then you can check all these edges to find the time difference and the MMSI difference to say if they belong to an encounter or not. And on the right-hand side, I placed another trajectory from a different timestamp, but very luckily, it just fits perfectly in between our encounter, which means that the Delaunay triangulation will actually create the edges between different vessels, is not going to consider the edges between circle and square, since it was able to partition the area just by using the middle one. that means that we will be using this, losing this encounter in the end due to the data like this. However, again, due to the sheer amount of historical AIS data we have, this trade-off was mostly welcomed, let's say. So this is the methodology that we have used to extract our encounters. And here you see some examples from the encounters that I've extracted for this MIU. On the first row, you see some head-on situations, and there are always two vessels, a blue one and a yellow one, vessel A and B. And you see some little, I don't know if they are quite visible, but some yellow squares on the boat trajectories. This is when the rules have been triggered. So on the first row, we have the head-on encounters. On the second row, we have the overtaking ones. And on the third row, we have the crossing encounters. Now that we extracted this data for this MIU, I wanted to prepare a simple machine learning model to see if we can use these encounters to learn when a vessel is going to engage in a maneuver, just by looking at the current situational picture between two vessels doing an encounter. For this, I used a maneuver extraction method that I have introduced in another MIU. So just as a summary, we have a method that we use in CML to extract maneuvers from historical AIS data. Here you can see that the blue line is the actual trajectory and the yellow points are the maneuvers that we extract using something like a cumulative sum algorithm. And after extracting the maneuvers, for each trajectory, I labeled the maneuver points as 1 and non-maneuver, the straight movement points, as 0. And before training the machine learning model, I did some data analysis on when do vessels start engaging in a maneuver. Here you can see a 3D graph. On one side, we have the TCPA in minutes and we have the DCPA in meters. And on the z-axis, we have the vessel count. Vessel count is basically incremented for a TCPA and DCPA if a vessel is engaged in maneuver for the first time during the DCPA and TCPA. So basically, I wanted to see at which time, at which distance and time to the closest point of approach a vessel thinks that it needs to engage in a maneuver. And we have seen that most of the maneuvers start between 0 and 10 TCPA, which means, by the way, time to the closest point of approach. So if you go with the same speed and heading, if both of the vessels go for TCPA amount of minutes, then you are going to be ending up with the closest point of approach. This is the meaning of it. And DCPA is the distance between the vessels during the closest point of approach. And we saw the maneuvers mostly start between 1,500 DCPA and 0 meters. As the average, we see that a maneuver starts when DCPA is around 1,000 meters and the TCPA is around 560 seconds, which also aligns with most standing orders that are given to vessels when to engage in an evasive maneuver. Afterwards, now we saw that the data analysis made sense, proved that the encounter data set may provide some good insight into predicting when an evasive maneuver should start. I scraped together a simple machine learning model where you see on the left-hand side the input of the data. Input of the model, which is DCPA in meters, TCPA in minutes, the distance between vessels, the actual distance at the time of measuring, the speed of own vessel, and the derivatives of the information, just to give it some kind of a temporal intelligence, let's say. And the model predicts safe time left to engage in a maneuver in seconds. Afterwards, I applied this model to our collision dataset. So basically, using the first 10 points of the collision, I predict a safe maneuver time using our model, which says you should engage in a maneuver at most in 700 seconds. And based on how much time elapsed and the vessel is not engaged in a maneuver, I assign a risk of percentage, which you can see here. And well, as expected, they did not engage in a maneuver in time when it was critical, which resulted in a catastrophic situation. And yeah, how do we want to further improve these models? Basically, this was a very simple model that I trained on all the encounters that I extracted from a certain part of German byte. And I trained it on 100,000 encounters or so from 3 months. However, we further need to develop models that are specific for different call rules. One model for head-on situations, one model for crossing, one model for overtaking, maybe. Or we may need to train different models for different ship lengths or different motor types of the vessels. The options are unlimited, actually. And now we also would like to make this data set public at some point for at least a certain part of it, so that it can be used by other researchers as well in the future. And with this, that was the end of my presentation. If there are any questions, I would like to answer them to the best of my knowledge. Just write them to the chat, or you can also open your microphone to ask them. Thank you.
Yes, thank you, Mert, for your presentation. And as you mentioned, if you have any questions, you can just put them directly in the chat, or you can also raise your hand and then you can also ask them directly. I think one intermediate question would be, since you mentioned the constraints of the Delaunay triangulation, why didn't we use anything else to represent the spatial hierarchies? I mean, there are a lot of other data structures suitable for this.
Makes sense. We could have gone with something like tree structure as well to create spatial queries. However, we decided to go with Delaunay because it was very fast in terms of computational speed. Thus, we wanted to have a quick proof of concept when extracting the encounters. And with this additional combining step, we believe that we overcame this limitation. But still, the tree structures could have been used to get rid of this additional combining step. I agree.
Yeah, and I mean, since you mentioned, we actually do a lot of investigations into optimizing also the computational part, since this is a lot of data that has to be processed.
Yes, that was the biggest challenge, in my opinion. Yeah.
And variable. Okay, if there are no further questions, you can also just write a mail to my colleague and ask him follow-up questions if you can think of something after the presentation. For our next MIU, our colleague Jonathan will give you a little bit of an insight into the current progress on the AutoFlex project and give a short recap of the first project half. With these words, I say goodbye. Thank you for attending our MIU and hope to see you next week for the next Maritime Innovation Update. Have a nice weekend.
Have a nice weekend. Bye.